Okay, so today we're going to continue talking about the broker pattern, focusing on the implementation of broker in the context of Android, as well as talking more generally about what it means to implement broker. And we're also going to talk about another pattern called the publisher-subscriber pattern. And we'll talk about how those things are realized in Android as well. So first, let's talk about the broker. If you recall, last class, at the end of last class, we talked about the broker, and I talked about how broker is a pattern that's used to shield clients from communication mechanisms and infrastructure concerns when they talk to services implemented in servers, which typically run in processes either on the same machine or in a separate machine. And we talked about how the broker takes care of all the low-level details, things like connection management, data transfer protocols, concurrency control, synchronization, threading, some fault tolerance thrown in there, memory management, all that kind of good stuff. That low-level stuff is sort of hidden from you and encapsulated by the underlying broker mechanisms. And so we talked last time about the good and the bad about the brokers and sort of the applicability and so on. And now what we're going to do is we're going to talk about how you might implement a broker. And of course, we're going to do it in the context of Android. So one of the first things you need to do is figure out what is your invocation interface going to look like. Now, there's a couple of different ways to ask this question. One way to ask the question is, what's the client application's interface going to look like, and do you want to make it as transparent as possible from the client? So if you want transparency, you're going to want to use some broker or some proxy-like mechanisms. We're going to get to that in a second. What I'm thinking about here is a little bit lower level than that. It's what's the interface that a proxy or an application that wants to program a little closer to the metal going to use in order to pass something to the broker itself. So how does a client invoke an operation on the broker? And so basically what we're going to do is come up with a way to allow somebody, either the client or the client's proxy, to pass a message from the client over to the server. And if you take a look here, you can see the way this is done in Android is something that's actually provided for by the underlying infrastructure, and it's this transact method. And transact is used to send the data. It's something that's exposed by the binder class, which is the lower level mechanism that does communication in Android, a lower level mechanism. There's lower levels than the binder. We'll talk about in a minute. But basically, it provides a method called transact, and you call transact with the code, which is basically the method that you're calling, as well as a parcel that contains the data that you want to have sent to the server, as well as how you want the reply information to come back. And so that information plus some other flags are actually used to send the data. And when somebody calls transact, which turns out typically to be the proxy that calls it, under the hood it ends up calling the onTransact method, and that will get delivered over to the server side, and there's an onTransact method that gets called back on the stub, and that's how the data gets upcalled to the server. We'll talk about that in a second. If you take a look at the binder code in Android, if you take a look at binder.java, you'll see this implementation, and it looks more or less like what I've shown you here. The next thing you need to do is you need to select and implement the marshaller. If you recall, there were sort of 3 or 4 main things you have in the broker pattern. You've got the client, obviously. You've got a requester, which is the client-side part that invokes an operation. You have the marshaller and demarshaller, which is responsible for serializing and unserializing the messages. And then you have this thing called a dispatcher. And those are the key pieces, and that's responsible for dispatching the request to the servant, which is what actually implements things. So the marshaller has different pieces to it, but this is typically what's handled for you by the proxy pattern. So I'm not going to talk a lot about here, because we just covered that in length in the proxy discussion. But in a nutshell, as you all know, the AIDL compiler generates the code to do the proxy operations, and it basically takes a look at the data types you defined in the AIDL interface, and then it creates the appropriate calls to the lower level Java code to marshal and demarshal things from native data types into these parcels. So as you can see here, for example, if we're using our download image stuff, then there's going to be this write string call here, which is going to go ahead and take the URL or the URI or whatnot. Oops, that should be URI. And it's going to go ahead and write that thing into the parcel, and then the parcel will be passed over as part of the invocation with the transact method on the remote binder. So we've already covered a lot of that stuff. What we're about to cover, though, now is a little bit deeper than what we covered with proxy. Proxy kind of stops at the point where things start to get interesting. So proxy is responsible for turning a method call into a message of some kind, a parcel in Android's case. But then it has to deliver that parcel somehow. How does it get there? Well, there has to be some kind of protocol to communicate between sender and receiver. And inevitably, these protocols typically use some kind of low-level byte stream or record-oriented communication mechanism, some type of transport. There's different choices, different middleware takes. It implements brokers. Some middleware uses datagrams or connectionless communication, where you don't set up a channel or you don't set up state on sender and receiver ahead of time. You just send the data out, and you either assume it gets there, or you don't care if it gets there, or you have some kind of retransmission protocol that is used at a higher level to make it get there. That's connectionless communication. Android doesn't do that. Much more common in certain kinds of middleware, especially object-oriented or non-object-oriented remote procedure call environments, is to use connection-oriented protocols. So the classic example of a connection-oriented protocol would be something like TCP/IP, where it sets up a connection and establishes state on both the sender and receiver, and then the data begins to flow. Does anybody know why TCP/IP sets up state on the sender and receiver in the kernel of the sender and receiver protocol machines prior to starting to try to deliver the actual data? What's the reason why the state is set up? First of all, does anybody know what TCP/IP does? Can someone explain to me what TCP/IP does?
It establishes a handshake between the two endpoints.
Right, handshake is established, but what's the handshake doing? What's it getting you? Why do we need it? Or what?
Sequence numbers, acknowledgement.
Reliability?
Right, exactly. The reliability is the reason. So if both sides understand the data that will be passed, then they can keep track to see if anything got dropped along the way by keeping track of sequence numbers and acknowledgements and so on. And by exchanging that information ahead of time and sort of pre-synchronizing on the starting sequence numbers and so on, then it makes it possible to not only route the information more efficiently, but also to be able to do it reliably. So if something gets dropped, the receiver knows it was expecting it and it didn't get it, and so there's a protocol that goes back and forth to try to retransmit the data if it gets dropped. And there's a whole bunch of other things that get added to TCP/IP to make it work in a variety of different networking environments. So that gives you reliability. That's what we use for the internet. In Android, we use a little bit lower level mechanism that's implemented as part of the OS kernel by something called the binder driver. And the binder driver is more of a kind of a proprietary is the wrong word, kind of a special purpose, customized protocol designed for high performance communication between processes that run on the same machine. And under the hood, it's implemented with some low-level system calls called IOCTLs or IOCTLs, IO controls. And there's a bunch of different sort of header information that gets passed back and forth. There's certain flags that get sent. This thing called binder write and read is a flag that's passed into the IOCTL call to inform that data is being sent back and forth. There's also a struct called binder transaction data that keeps track of a bunch of fields, things like what the buffer is that contains the bytes and some other information that is used by the lower level binder driver transport to move the information back and forth. And so that's kind of what's going on under the hood. This is not something you would typically use in a networked environment. It's really intended for the relatively low latency backplane that you would find if you're running in the same device. It's sort of optimized for that kind of a world. There's a nice paper that you could read about, or a nice presentation that I have a link for here that gives a lot more information about the low-level details of how the binder driver is implemented in Android. It's actually part of the Android Linux kernel extensions. Now, the next thing I'm going to talk about here, I colored it red because it doesn't apply directly to Android, but most broker implementations are running in, or many broker implementations are actually running in a networked environment, not a standalone backplane connected by a bus environment. So if that's the case, you have to have some kind of network communication. And there's a bunch of things you need to think about in that case about the protocols you use to talk across the network, which are often TCP/IP based, and then other just mechanisms you might want to add, things like acceptors and connectors and reactors and so on. And these are things we're not going to really cover here because Android doesn't have that capability. But if you start studying networked communication and networked programming environments, things like ACE or Python's Twisted or other parts of Java like Jetty and Netty and so on, you'll find lots of examples of these kinds of patterns used as part of the network communication layers. But we're not going to really cover them right now. The next thing you have to think about if you're trying to build a broker is think through the issues related to resource management. So resource management is an important part of any system, especially as it scales, because you want to make sure that these resources that are in high demand but somewhat scarce supply are properly allocated and deallocated by something, the operating system, the middleware, or some combination. And the key point here is that you don't have an infinite amount of this stuff. What are some good examples of resources that you don't really have an infinite amount of in the context of a broker or some kind of communication system?
Ports.
Ports, great example. So ports are typically endpoints of communication that queue up data that goes to them. They're addressable somehow. And you don't have an unlimited number of ports. You'll eventually run out. Of course, why do you eventually run out of ports? What's the other resource that you only have so much of before you run out of it? Memory, right. So there's only so much memory. So you have to manage memory. You have to manage ports. Other things you typically want to manage would be connections, which are often related to ports. Threads, that's a big issue. You don't want to have, don't want to start spawning threads just endlessly because you will quickly run out of them. And if you don't run out of them, you'll run out of memory, and then you'll have all kinds of thrashing and problems like that. So there's a bunch of different patterns that people have used over time to implement effective resource management. And these are protocols, these are services, and so on. So some examples that you might want to use in the context of a broker would be things like caching and pooling, which at first glance sounds similar, but they have a little bit different purpose. So oftentimes we use caching on the client side in order to have information held open even if it's not currently being used. So a good example of a cache might be some kind of connection cache, where you might share a connection to a server, and as you allocate those connections, you might cache them on the client. So if you have multiple threads that are trying to write, they can share access to the cached connection. So that's one example of something. A pool might be something like a pool of threads, where you pre-allocate a bunch of threads, you have them running, say, on the server side, and when a request comes in, the incoming binder driver picks a thread out of the pool and gives it the work to do. So pooling and caching are really both designed in order to pre-allocate and or allocate and remain allocated resources so that things don't have to be set up and torn down from scratch every time, thereby improving overall throughput. So a good quiz question would be, what are some examples of resource management, and what do they buy you in the context of the broker pattern, or something like that? There's some publications you can see. These appeared in the POSA 3 book. You can also take a look at them on the website of the authors of the POSA 3 book to talk about pooling and caching. Another thing that you need is some kind of registration interface that's used by the dispatcher to be able to register and unregister servants. Servants, keep in mind, are the things that actually get requests dispatched to them by the underlying broker middleware. So in the context of general purpose distributed computing, people have defined things like object adapters to do this kind of stuff. In the context of Android, we have something that's called the binder. And one of the methods that the binder defines is called attach interface. And you pass into that some information about the interface, and this gets stashed away so you're able to know about it, and you can find a way to get back to it later when you need to do callbacks on it. And you can take a look. All the source code is available here. Another thing we need to be able to do if we want to implement a broker is figure out some way of being able to communicate between the client and the server so the client gets access to the servants that the server is managing and owning. So how do you communicate that information back and forth? There's lots and lots of different ways to do this. In more traditional distributed broker environments, you typically use some kind of naming service or some kind of dictionary or directory service to be able to map names to object references or something else. And that's needed because we oftentimes need to be able to look these things up more like you would search things with a Google search. You want to type in some properties, and then you get back a bunch of options, and you choose one or more of them to invoke. In the case of Android, it's a little different. It's a little bit more tightly coupled. So there's a protocol that's defined here that has a couple of parts to it. One part is the onBind factory method that's defined by the server who implements the binder object, and that is responsible for giving back to the caller which is ultimately going to be the client, a reference, an iBinder to the binder. So iBinder is an interface to a binder, and you can use it to invoke operations. And you can take a look at the service interface to find out more about that. The other thing that is defined on the client side is a hook method called OnServiceConnected to get this binder back from the server or the service and then stash it away someplace on the client side so it's available for being used to invoke these two-way operations or one-way operations later. So there's kind of this multi-step protocol, as you may recall, where you do a bind service that causes onBind to get called on the server. That passes you back a binder object. That binder object comes back to you through OnServiceConnected, the hook method. You get that thing, and then you can use it to invoke operations. So that's how Android gets the information back to the client. And you can take a look here for more information about the service connection interface. Another thing we need is some kind of mechanism to be able to transform these request messages that are coming in from the requester into upcalls that are dispatched on a method defined by our servant. Now keep in mind, in the case of Android, the servant is basically whatever typically anonymous object subclass is anonymously from stub, and then fills in the various methods that have been defined on that stub in order to carry out the work that was described in the AIDL interface. So in this particular case, this is handled by the stub. When the generated stub comes out, it has an onTransact method, and that onTransact method will take a look at the particular code that was passed over by the transmit or the transact call, and that transact call will then end up dispatching the onTransact callback, which looks at the code, which tells it how to demarshal the various fields that are passed over in the parcel, and then that's turned into native data types in this case, which are then passed to the upcall method to the actual servant implementation. In this case, we're doing the download image method for our download interface, iDownload interface. So that just gives you a sense of how those things fit together. So that kind of illustrates all the different pieces that are involved. Client invokes a method on a proxy. Proxy turns the method into a message, calls the transact method to pass it down to the broker through the requester portion. The requester sends it across using the binder driver communication protocol, comes up on the receiver side. The dispatcher receives the request, takes a look at it, figures out who it's for using the lookup mechanisms that were defined by the registration interface we looked at, and then ultimately finds the right stub, and then invokes the operation on that stub to go ahead and call back on the servant's implementation method to get the job done. So that's kind of the steps involved. And then there's also a reverse order going the other direction if there's a reply. Something else you need to do if you want to start implementing Broker is figure out whether or not you're going to support asynchrony or just simply stick with synchrony. Traditional brokers tended to only support synchronous communication because they were trying to mimic two-way procedure call interfaces. So a regular procedure call is a two-way call. So for many years, remote procedure calls were kind of two-way calls. And early versions of Corba were like that too. And if you didn't like that, you used kind of one-way calls, but that had some downsides. Later on, people began to realize this is kind of limited. We really want to support asynchrony as a first-class citizen in the type system of the broker. And so people started adding new support to that. In Corba, they have something called asynchronous method invocation, for example, and asynchronous method handling, which are used to be able to give you better support for asynchrony. Microsoft COM has something similar along those lines as well. In Android, they don't really build it in directly, but you can do it by pattern convention, where you pass a callback object to via a one-way operation on the interface, the IDL interface. That goes to the server. That callback object is stashed away somewhere and then is used later, either in the same thread or some other thread, to invoke a one-way call back to the client. So you have to decide how to do it. Android doesn't really give you a lot of sophisticated support for this, but it is possible to do it, and I find it a very useful feature. And then the last thing to think about if you're trying to implement a broker, obviously there's more stuff than this, but this is the key things to think about, is whether or not you want to try to do colocation optimizations for cases where you're invoking a method on something that's in the same address space as the caller. So if you end up having your servant in the same address space as your client, do do you want to do something to match those things up? And as you can see, the generated methods called Asynchrony actually have some checks to see whether or not the call that's coming in is actually resolvable in the same address space as the client. And if it is, it just returns back the interface directly to the caller, and you can invoke a method call and it goes straight to that thing. If it's not co-located in the same address space, then it ends up making a proxy and returning the proxy. And when the proxy is called, that does all the things a proxy does to do the marshalling of the data and then the transmission of it through the binder mechanism and the binder driver and so on over to the receiver side. Any questions about any of that? Some more information here at this link about colocation optimizations, just talking about the overall concept and showing the speed-ups involved. So now that we've kind of seen the broker pattern implemented in various steps and kind of walk through how Android does it under the hood, let's give some examples of some pretty cool, sophisticated uses of the broker pattern in Android itself. So this particular example uses the network settings activity. You can see here, thanks to Christoph, we have a screenshot that he managed to purloin through tortuous path to get a screenshot of what this app looks like. And basically what it does is it goes out and it searches for cellular networks like, CDMA or GSM or multiple providers, which you may or may not have depending on what kind of service you have, if it's locked, unlocked, carrier provided, where you are, and so on. But basically, here's what it does. There's a activity side of this thing called network settings, and that invokes start service, and that causes the activity manager service to go ahead and start up the network query service using the activator pattern that we talked about before. And then that goes ahead and initializes that particular service. And then here's kind of the quirky part. Right after it calls start service, the network settings activity then makes a call to bind service, which is a little weird because it's kind of this Frankenstein monster that's a little bit of both worlds. It's a started service, or the network query service is both a started service, because start service was called, and a bound service, because bind service was called on it. And the basic idea, the basic reason that they did this, does anybody want to hazard a guess as to the reason why they actually did it this way? What was the reason, what was the motivation for this in Android? Yes, sir?
Bound services die when there's nobody else that's bound to it, but if you start it first, then it's a started service, so it's not going to die unless it has to.
Right. So they wanted to be able to keep this service running around even if nobody was talking to it, which is kind of funny. That kind of flies in the face of a lot of what they say in Android about not doing this, but this is sort of a systemsy service, so I guess they figured that it was okay for having it running there in the background and consuming some resources. So yeah, that's exactly right. So start service causes it to be launched, and because it was started, it won't shut itself down automatically. But they wanted to be able to make AIDL calls to it, so they used bind service in order to get back the appropriate binder mechanism. Now, there's some other things they could have done to do that, but that was the most straightforward way to do it. So that calls the onBind method, which goes ahead and grabs the binder, returns it back by the callback to OnServiceConnected, and it goes ahead and OnServiceConnected actually turns around and invokes a method called loadNetworksList, which is a method running in the activity. And this method turns around and calls to the mBinder object in the service, and it invokes the startNetworkQuery method, which is a one-way call. And then that goes ahead and starts this lookup process where it's checking to see whether or not the underlying network service is changed or what it's doing. And this actually requires some sort of registration with the low-level radio interface layer service mechanisms, which will actually deliver results back via handlers at some point down the road to the network query service. And when this stuff comes back at some point down the road, then there's another callback that takes place in the handle message callback, which is being driven by low-level stuff from the radio interface layer. It invokes a callback to invoke the onQueryComplete method, passing back the list of network providers that are out there, which are then displayed so you can see what they look like. So it's just this really interesting, totally asynchronous use of the broker pattern, illustrating activator, illustrating proxy, illustrating the broker, all this stuff that we've been talking about all comes together, and it's basically using an asynchronous communication mechanism to make everything work together and not block anything. One of the most important reasons why you would use asynchrony, of course, is to avoid blocking, because that's a downside where you don't want the main thread of control to block. Okay, so to summarize the broker, you have support in Android via the binder and AIDL for broker. You have support for started services, which use the command processor pattern to do message passing. And in some sense, then broker and command processor are pattern complements. You can use them in different purposes. They sort of compete with each other. And as we talked about last quiz, you would choose one over the other depending on the circumstance in which you find yourself arising. It is your job, or the job of whoever you work with, to understand the trade-offs between these patterns. And one of the nice things you get from understanding this stuff as patterns, as opposed to just understanding them in terms of the features that Android provides, is that it gives you a bird's eye view of the trade-offs between architectural alternatives. And ironically enough, as you switch between platforms, as you switch from Android to iOS, as you switch from smartphones to clouds, or whatever you move to, you'll find that these patterns exist in almost all those different contexts. And once you understand the design alternatives and trade-offs in terms of patterns, it's a heck of a lot easier to navigate through the design space. Whereas if you understand them only as specific details of one platform, like Android, or Jetty, or Netty, or Corba, or DDS, or whatnot, then as you start moving around, you'll have to relearn everything from the details up, which takes a long time, and you may miss some of the important commonalities that exist there.